Welcome back to a new video about LC ladder filter design. We start with our third example, and this is our Butterworth response again, and we will design a high-pass filter. Of course, we will work out the calculations step by step, and we'll also verify these in SPICE simulations. So the objective is design a Butterworth response filter. It must be a passive LC ladder filter. It must be a high-pass configuration or high-pass filter. It must have a 50 ohm double terminate shunt input circuit. That means looking at this generalized circuit, you can see the generalized filter block. The source resistance must be 1 ohm and also the load must be 1 ohm in the normalized configuration. And then we need to scale up these RS and RL to 50 ohm, so we need to use the magnitude scaling factor of 50. That is to be determined shortly. The specifications for this design is the maximum passband ripple of 0.5 dB given by A max. The minimum stopband attenuation must be 25 given by A min. And we have also the passband frequency of 80 kHz, so FP, and a stopband frequency FS of 10 kHz. Remember, in the low pass filter design we have the passband frequency which was smaller than the stopband frequency. Now it's flipped because also the body plot for the magnitude is also flipped. Okay, let's look at the solutions and also determine how we can design this circuit and also determine the component values in our final form. Step 1 is the calculation of the filter order. That is really similar to the low pass filter example. So we start with epsilon P and also the epsilon S. Epsilon P is related to A max by this formula. You just substitute this 0.5 dB in here and you calculate your epsilon, which is required for the passband region. For the stopband region, epsilon S again, but then for the A minimum, you substitute the values, you get now here 17.755. Now taking this together, we now calculate the filter order using this formula. This formula is similar to the formula of low pass filter, but the only change is the denominator here, where you have log of FP over FS instead of Fs over Fp. So that is now for high pass filter. The numerator is the same, so you just substitute the values of the given Fp and Fs, and also what we have calculated for the epsilon P and epsilon S. These are the values and you get now 1.889, and we need to use integer values for our filter design because you cannot have a first order that is way too long, way too small here. The second order is actually what we need minimum, that means n is 2. So we move on with n is 2. The second step is calculate the frequency scaling factor, Kf. That is also the cutoff frequency in this case. The Kf is similar again as the low pass filter. In this case, the epsilon P is to the power of 1 over n instead of minus 1 over n. That is the only difference. The rest is the same. The omega P here is again that 2 pi times the Fp, so we need to do 2 pi times the AD kilohertz. So when you do now the calculation, you see here the 2 pi times the AD kilohertz times the epsilon P, which is calculated, and 1 over n, which is 1 over 2, and then you calculate it here, you get now 297.1 kiloradians per second, and that is then approximately 47.28 kilohertz. Okay, we need this information later for our component values. Now, step 3 is to calculate the scaled component values. That is actually our values of our filter. This is the table we will use for our Butterworth response, and we have a second order. That means we need to use this row here, which is now given here in this region. That's now the x1 and x2. Those are the component values in the unscaled version, so actually the normalized. So that's also what we see here, normalized. So we can see that this circuit is required for this Butterworth response. We see the RS, which is a normalized value, RL, which is a normalized value, both are 1 ohms, so we can see it here. C1 and L2, that's just the numbering order. C1 in the normalized value is 1.4142 farads. And L2 here, also in the normalized value, is 1.4142 henries. Now we of course need the practical value, so we can then move up to the scaling of these components C1 and L2, RS, and RL. For that, we need a prime. So you see here the prime value, RS prime, and also the RL prime. But remember here, compared to the low-pass filter, the components, the capacitor here and the inductor here are actually flipped. So the capacitor here will turn into an inductor, which is now called LP1, which is sort of the parallel form. And the inductor here is formed into a capacitor in series. So we sort of have flipped in the component values. That is not the case in low-pass filter. Low-pass filter just use the capacitor here and also turn it to another value of the capacitor. But now you need to replace the components also. So that is an important difference between low-pass filter and the high-pass filter design. So let's look at the formulas. The parallel here, the parallel inductor LP1 is related to C1, which is this 1.4142, is given by this formula. So Km over Kf and over C1. So the C1 again from the table. The 50 is, by the way, again our magnitude scaling factor. You see the 297.1 times 10 to the power 3, which is this kilorad radians per second. And also our C1, which is our normalized value. And we now do the calculation, you get here 119 microhenries. Now for the capacitor CS1, which is the series part of the capacitor, which is related to that L2, you see that here that's given by this formula. It is actually very similar to the others, but in the low pass filter, the C was here, and for the L was actually in the numerator. So the only change is that it must be flipped in order to change the capacitor to an inductor and the inductor to a capacitor. Now again, the Km must be 50. Why again? Remember that 1 ohm must be turned into 50 ohm. That is given in the objective. So we just substitute values of 50 for the Km, Kf as shown here, and also the L2, which is in this case the same, a normalized value. When you now calculate it, you get now 47.6 nanofarads. Now the only thing is RS. RS is just RS prime in this case is just the scaled up version of the RS normalized, which is then times Km. So Km is 50, RS itself is 1, so you get 50 ohms. Similar for RL prime, which is then Km times the RL. Again, 50 times 1, 50 ohms. Now we have all the components we require for our design. Okay, now looking at the circuit we have designed, this is our circuit for in the simulator. You see the RS in the normalized values, RL, L2 and the C1. This is the output of the LPF, which is a low pass filter unscaled. That's the prototype filter. Now we need to convert those to a high pass filter for our design. You see the C1 is changed to LP1 and L2 is changed to CS1. And you see the values we just calculate also in the circuit here. So remember, we transform our low pass filter into a high pass filter by this transformation. And this is the scaled version now. So we will use this circuit here to and verify this, that our specifications are correct or met. So the simulation results, we look directly to the body plot magnitude condition. This is the magnitude plot. You see the passband gain of minus 6.02 dB. This is again the circuit here. So let's go one by one to specification. Why is this minus 6.02 dB? Because if you look at the circuit and at high frequencies, this is an open conductor and the capacitor is almost a short, so you get actually attenuation of 2 or a gain of 0.5. That means 20 log of 0.5 is minus 6.02 dB approximately. So that is the reason for this passband gain. Now we also need the passband frequency, stop band frequency, also the stop band attenuation, and also the ripple at the passband. So all of them needs to be checked. Looking at the next specification, passband frequency, you see that passband frequency is 80 kilohertz. Why is this correct? Because when you go down from minus 6.02 dB to minus 6.52 dB, which is 0.5 dB down, which is of course our A max, then you reach the 80 kilohertz, which is as we wanted. Looking at the next specification, the stop band attenuation, at the 10 kilohertz here, you see that we have a gain of minus 33.02 dB. So how far are we going down? We started at the flat line is minus 6.02 dB, so you go down to minus 33.02 dB, so the difference is 27 dB exactly. Is this enough? Now looking at our stop band attenuation, we require minimally is 25, so 27 is definitely more than enough. So that's also met. The final one is the cutoff frequency. The cutoff frequency is, in this case, from the specification, from the simulation, I must say, is 47.29 kilohertz. We have calculated using the frequency scaling factor 47.28 kilohertz. So it's very close to each other, just do the rounding of errors, so we can say this is also perfectly fine. So we have designed our circuit according to the specification, so we can say this circuit will do the job. If you have any questions, comments about these examples, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.